First Flight kickoff streams. My name is Jess, and today we have another very exciting project for you to dive into and practice your security auditing skills. Now, these contests are designed for you to test what you've learned over on Updraft and see if you're ready for the big world of competitive audits. First Flights reward you with XP, so they are just for practicing your skills, and they can be used to get involved with the community, learn from each other. Now, this week's First Flight is actually written in Vyper, so it's specifically targeted to those who have taken our Vyper and Moccasin courses that were new to Updraft just 1 or 2 months ago. But even if you haven't completed those courses yet, you can still dive into this code base and see what you can find. I would really, really urge for you to not shy away from learning new languages, because it's a brilliant skill to have, to be able to adapt and learn different languages, and it increases the amount of opportunities that you've got within the space. So anyway, hopefully you can hear me. My mic should be closer to me than that. Anyway, let's take a look at the repo. Let's take a look at the contest and see what this week's First Flight is all about. So let's take a look at this page. You can find this by going to codehawks.com and then hitting First Flights at the top here. And this week's is called Vyper Vested Claims. So this smart contract is designed for distributing tokens with a vesting schedule. The contract uses Merkle trees for claims, allowing 31% of tokens to be released at the TGE and the remaining 69% to be released linearly over time. So we've got this chart up here just to explain this for visual learners. What we can see here is the amount of tokens in circulation is 0% until the TGA, the token generation event. At this point, the amount of the circulating supply will increase to 31%, and then it will increase linearly over time. So if a user comes along and they are invested and they can redeem some of their tokens, they'll be able to redeem a different amount of tokens over a period of time. This is to stop too many tokens being in circulation in one go. So a user may come along, and if they have the rights to claim some of these tokens, they can come along immediately after TG and claim 31%, or they can come a couple of days or weeks after, however long the vesting schedule is, and they will be able to redeem some more until finally the vesting schedule time frame is up and they can redeem 100% of their tokens. Now, this repo is using Merkle trees, and we will discuss that within today's stream. And I will refer you to some different articles to have a look at, videos to have a look at, to help strengthen your knowledge of Merkle trees, because they are mathematical, slightly more complex, but there's nothing that you can't achieve by looking at the Updraft curriculum. Let's take a look anyway at how we can get ourselves set up for this repo before we really dive in. So when you are on the CodeHawks platform, you can just click through to view repo, and you will come to this page. Now, if you go to here and you copy the URL to clipboard, you can open your VS Code. That is the wrong VS Code. Here we go. So you can open this, open a new folder, whatever you'd like to do. And then in your terminal, all you need to do is a git clone and then copy this in here. I'm not actually going to do that. We are then going to just run mocks test. And when you've done that, you should be all set up. There's no dependencies to install for this repo, so you should be all good to go. There are quite a few tests written in here to help you along the way. This should help you with your proof of concepts as well. And so we're all set up there and ready to go. I'm not going to do that because I have already done so, and I've added some comments to the repo, and I don't want to have to start all over again. So this is the repo all set up in your VS Code. There are instructions on the CodeHawks platform as well for getting started. But to be honest, it's very simple. It's just run mocks test once you've cloned the repo. So there we have it. We are all set up and we're ready to take a look at the code base. Now, as I said, this is a Vyper code base. I wouldn't shy away from it if you haven't seen Vyper before. It's basically Python, but for smart contracts. It's definitely something to look into if you haven't looked into it already. A lot of Web 2 developers use Python, so Vyper could be the language that really helps us get adoption within the Web3 space, and it could become a lot more popular within the next couple of years. So it's definitely worth doing your research and learning Vyper. Now, as I've said in a previous First Flight live stream, don't shy away from new languages because the security practices are still the same. Yes, different languages may have different things in place to restrict vulnerabilities from happening, but overall, the languages don't really change the vulnerabilities that can be found. A lot of vulnerabilities that are found within competitive audits are due to the actual intended functionality not being correct. Yes, there are some that are like a reentrancy attack, a denial of service that you will see over and over again, but a lot of vulnerabilities come from actually understanding the intended functionality and seeing where there's a slight mistake or a way to get around it. And that's the same in any language that you'll see, whether it's written in Solidity or if it's written in Vyper, the vulnerabilities for those kinds of events will still be there. So just looking at it in a different way and understanding how the code is written, you'll still be able to find those vulnerabilities. And first rights are a brilliant place to start if you're looking at new languages. So these contracts are written in Vyper. Don't shy away from them. Get involved, and you'll have all of the support from the community within the Discord as well. Now, before we get into the contracts themselves, I would like to say, if you have any questions during this live stream, then do pop them in the live chat. And if you have some questions at a later date, then head over to our Discord, which is linked in today's description, and you can ask questions in there. There is a channel open specifically for this contest, so you can ask questions and learn from each other's questions as well. Somebody may be asking a question that you haven't even thought of yet, and the answer could help you on your journey to finding some vulnerabilities. Now, when you do find those vulnerabilities, you can submit them on the CodeHawks platform, just like a standard contest, and they will be judged by our judges at CodeHawks, and you'll be able to see if you're successful and if you weren't, and how you can improve for some real contests in the future. Now, let's take a look at these contracts. Let's get started. First of all, explaining again, this is a project that is going to allow 31% of tokens to be released into circulation on the TG event, and then other tokens to be released linearly over time. So first of all, what do we need to do? We need to set up an ERC20 token so that that token can be released over that schedule. First, so this is what the token contract is here. It imports and implements the standard ERC20 interface. So if you have done the Vyper and Moccasin courses, it's probably not something you haven't seen before. This is set out in the standard way. So you are going to have your state variables, your name, your symbol, your decimals, total supply, balance of mappings, and your allowance mappings. So as you can see, the top couple are strings, and then we've got some uint8 and uint256. Then we have these mappings here. So the balance of state variable is a hash mapping storing each user's balance, and the allowance state variable is a hash mapping of allowances. So this sees who is allowed to spend whose tokens. Moving on from those, we then go into the constructor. This init function is the constructor. So this is run once the contract is deployed immediately. And we are going to define some of these state variables that have been highlighted up here. So we are going to set the supply to 1 million tokens with 18 decimals. We are going to set the name of the token to token. We are going to set the symbol of the token to TKN, and we've got those 18 decimals. Then we are moving on to the supply. So the total supply of this is defined as supply, which is defined later on. And then the balance of, so we are basically saying in this line here, all of the supply is going to be given to the deployer on deployment of this contract. And then we are going to an emitted event to say the entire supply has been given to that deployer there. So that's just the constructor, similar to how you'd see in a Solidity contract. This is how the constructor is laid out in a Vyper contract. You will see as we run through these contracts that the format is the same, it's just the actual language that is different. Moving on then to the ERC20 functions, we've got the update function, we've got the transfer function, all kind of bog standard. Then we've got the external functions as well. Again, very standard. The transfer from, approve, and burn functions are all within there. So this is your standard ERC20 token, but Vyper style. You can run through this. There may be some vulnerabilities in there. So definitely take a look at the whole repo. Both of these contracts are in scope, but that is essentially a standard ERC20. And then we need to look at how these contracts are vested and how they are sent out to those users that have invested. So this is where we get interesting. This is where we are starting to look at the Merkle trees, a little bit more mathy and a little bit more technical, but not something that you won't be able to grasp if you've completed Updraft. So let's take a look at what is going on here. So we are first of all using this contract to distribute tokens to users, 31% on TGE and 69% linear vesting. Before we get into the actual contracts here, I want to run through how Merkle trees work. So I've pulled up a example here. So this is a Merkle tree. This is what they look like. So you have the root hash, and this will be defined by the contract deployer. And then you have lots of hashes underneath. So just to explain this very quickly, we use Merkle trees to determine if a piece of data is in the struct without running through it over and over again. So we'll be able to see if a user's address is eligible to claim some tokens by using the root hash, as opposed to running through an array over and over again. So to prove that an address is within the Merkle tree, we can provide an address, we can provide some other data, and if we come out to the same root hash, then the address is able to claim tokens. So how this is all set up is this will be determined prior to the root hash being set by the deployer. So we can say, look, we have 4 users and they can all claim tokens. They're all eligible to claim tokens. Well, we then create a root hash and then we give the contract that root hash, and then the contract can check, hey, is user 1 able to claim tokens? Yes or no? And then a different user may come along, user 5, and they may try and claim tokens, and we'll say, actually, no, this doesn't work out. The Merkle tree shows that their address isn't part of the claimable addresses array, so we should not allow them to claim tokens. I hope this is making sense. So how do we determine if a user address is able to claim tokens or not? Well, how a Merkle tree works is we get a user's address, we hash it, and we get another user's address and we hash that as well. Then we hash both of those addresses together, and then we hash this with another hash until we get to the root hash, and it breaks down as follows. Now, the amount of users will obviously increase over time. We're likely not going to have just 4 users, but this is a simplified version. Now, to determine if a user is part of a Merkle tree, what we need to do is we need to provide the contract with the actual user's address that we are testing for and a number of other hashes, the intermediate hashes, to allow us to generate the final root hash. So what this contract will be doing over time is they will take the user 1's hash and they'll take user 2's hash. They'll hash user 1. They'll hash that with hash 2, and they'll have hash 1 too. And now we've also provided hash 3, 4, so we can hash those 2 together and get the root hash. Now we can confirm that the root hash is the same as the contract's root hash by just comparing those 2 together. If, however, we were to provide the contract with user 5 and we were saying, look, here's user 5's address, we're going to provide this, we'll provide this one, we'll provide this, and we'll provide this. Once we hash this, we're not going to get hash 1, we're going to get something different. And when we hash that with hash 2, we're going to get something different here. And when we hash those together, we're going to get something different up here. So when the contract compares the actual root hash to our root hash, it will be different, and we'll say, no, this user isn't correct. They cannot claim any tokens. So that is how the Merkle trees work. I hope that's been explained well. Kira has done a brilliant video on Merkle trees that you can find on her YouTube channel. I will link that actually in our stream right now, so you can take a look of that. It will be very, very helpful for you when you are taking part in this contest. So let me just search that and get that up for you. Now, when we're looking at this, you may wonder, why do we need to use Merkle trees? Why can we not just go to our VS Code? Hold on. Why can we not just say, hey, look, examples loop loop dot sol. There we go. Why can we not just say, hey, look, here's an array of addresses. Let's make it public. And we're going to call it addresses. So these are the addresses that can claim tokens. Why can we not just have a function that goes through, takes an address and goes, let's make it public. If I could spell correctly, we'd do this a lot faster. Why can we not just have a function that says, look, for uint 256, when we have start with 0, why can we not just loop through that array, addresses.length, and check to see if the address at a specific point is equal to the actual address that has been inputted into the function, and then we do the transfer or whatever we need to do there. Why can we not do that? Well, if we were to do this, we would have denial of service. We would see that the cost to actually run through this array would become very, very high if the list of addresses that can claim tokens becomes very, very large. So we'd get denial of service and it wouldn't work out. So essentially, we're going to use Merkle trees instead, because this is going to allow us to check for multiple addresses on a much easier. So I hope that has made sense. Please ask some questions in the live chat if you have any questions about this. Once again, just running through this very quickly, we hash all of the data together through each of these lines until we come to a root hash. This is done once we have the list of users that can claim tokens. So the deployer will say, this is the root hash for this contract. This is the data that we will use. And then if we want to check if an address is eligible to claim tokens, we need to provide the user's address, some intermediate nodes hashes along the way, and then the contract will hash it all together and make sure that the root hash of the data we've provided is the same as the contract root hash that's been provided by the deployer. I hope that's made sense, but please let me know if you have any questions. Taking a look at the actual contract here then to see how this is written in the code, you can see here, first of all, we have the constructor, we need to be in the vested airdrop. And you can see here, we have some state variables here, the vesting start time, the vesting end time, the Merkle root, the token, the owner, and the claimed amount. So the vesting start time is going to be when we are starting from TGA. We have that linear vesting period, and then we have the vesting end time as well. So when 100% of tokens are claimable and the vesting is complete. We have the Merkle root, so that is the actual root hash at the top of the tree that will be used to compare against the hashes that are generated in the contract to ensure that they're the same and that users are able to claim some tokens. We also have the token address as well from our token contract. And we have the owner's address as well, because the owner in this repo does have some special rights. If you take a look at the CodeHawks platform and you go to the contest details, you can see there are two different actors within this contract. You have the contract owner, so they can set the Merkle root, determining who is able to claim tokens, and you can they can also rescue tokens in emergency situations as well. We will come on to those functions a little bit later. With the users of this contract, they will be able to claim their vested tokens, but they must provide a valid Merkle proof to claim tokens. So they must be able to provide an address that is eligible and the intermediate node hashes for the Merkle tree to be generated and to come out with the same Merkle root. So taking a look back at the functions here, we have the owner's address that will be inputted, and then we have the claimed amount. So this is a mapping that tracks the amount each user has claimed so far. We have some of your standard events before we hit the constructor, which is going to define a lot of these state variables. In terms of events, we've got the claimed event that is emitted when a user successfully claims tokens. We have the Merkle root updated event. This is emitted when the contract owner updates the Merkle root. We have the tokens rescued event, and this is emitted when tokens are rescued by the owner. So they're the three events that we have within this contract. And let's move on to the constructor now. So this is where, as I said, we are defining a lot of the state variables that were stated up here. So we've got the Merkle root, we've got the token, we've got the vesting start time, vesting end time. We are setting the owner to the deployer of the contract, and then we are going to log those changes there as well. Moving on then to some of the functions here, we've got the only owner function. So this function is used to restrict access to only the owner. So we are asserting that the message sender of any of the functions with this function are only called by the owner of the contract. So this is used throughout the functions below. If we take a look here, you can see it's used within the set Merkle root function and within the rescue tokens function, which were the two things that we mentioned were limited just to the owner. Continuing on though, we have the hash pair. So this function is used to hash a pair of bytes 32. This will be used when generating a Merkle root to compare with the Merkle root provided by the deployer. This will also always hash two different bytes 32 together and provide and create another bytes 32. We also have the verify proof function. So this function is used to verify the Merkle proof. True if the proof is valid and false if the proof is invalid. We have the verify proof function. This function is used to verify the Merkle proof. So we have so this one has a underscore before and this one doesn't. So the differences in names there. True if the proof is valid, and again false if the proof is invalid. These functions obviously rely on each other. You may have seen this frequently with the underscore being before the function name. So this function will call upon the function above to run through. Then we have the calculate vested amount. So we are calculating the vested amount, and then the titles are very self-explanatory here, but I hope this is helpful in some way. We are going to take a UN 256 at the total amount, and we're going to run through this. Then we've got the set Merkle root. This is restricted to only the owner, as discussed before. We've got the rescue tokens. This is again restricted to only the owner, and this is meant to be used in extreme scenarios in case of emergency. As the developer has put here, this is better safe than sorry function. Use it only in emergency. It can only be called by the owner thanks to calling this function that we defined earlier. And this will transfer all of the tokens to the deployer just to save tokens in case of emergency. And not finally, next we have the claim function. This is an external function again. So this takes the user's address, the total amount, and the Merkle proof. And what they are going to do here is return true if the claim is successful and false if the claim is unsuccessful. Finally, we have the claimable amount function. This is again an external function. It takes the user's address and the total amount UN 256. This function is needed for the front end to show the claimable amount, and this returns the amount claimable for a user. So with the actual functionality itself, it's pretty straightforward, but it is important to understand Merkle proofs to understand how this is running. I think this is a brilliant code base for you to take a look at because it will help you understand Merkle proofs on the most basic level, which is brilliant because learning more math and how functions work is always great. Learning how to avoid a denial of service attack is always great. And this is a pretty common way to avoid those rather than looping through an array multiple times as we discussed earlier. So those are the two contracts that are in scope for this repo. As I said at the start, there are no dependencies, so you can just solely look at, how can we make a vesting contract? How can we use Merkle proof? This is a brilliant place to start if you're wanting to learn more about the math involved in smart contracts. I would 100% recommend to take a look at the video that Kira has made on her YouTube channel. I have linked that in the live chat for today's stream. It looks like we don't have any questions in the live chat about the repo, so no worries about that. But if you do have any questions over the next couple of days, this contest is live until next Thursday, I believe. It ends in 6 days. If you have any questions over that time period, then do head over to the Discord, which is linked in today's description, and you can ask questions about the repo in there. There will be others who are beginners, others who have maybe completed a couple of first flights by now, or maybe others that just want to get involved with Vyper for a first flight. So there'll be a range of experience in there, and you'll be able to all help each other, hear each other's questions, and learn how to find some vulnerabilities in this. Ruderanth says, for learning Vyper, we have to learn Python. It's very much helpful to understand Python first, which is why within the Vyper course on the Updraft platform, we do run through some Python before we move into Vyper. Vyper is a very similar language to Python, and Python is used commonly in Web 2. So the hope is that Vyper can help onboard users from Web 2 to Web 3. Now, it's not a necessity to understand Python. You can just go straight into learning Vyper. That is not a problem at all. You will have seen throughout the stream today that if you understand Solidity, you'll understand how the differences between Solidity and Vyper, and you may want to take the step across that way. As I said, when it comes to being a security researcher, the language itself shouldn't matter too much. Just understanding what the code is doing and how what its dependencies are doing can really help you find those vulnerabilities. So with that in mind, I think we are ready to close off today's stream. If you do have any questions, as I said, head over to our Discord. I hope this explanation has helped you all and given you a head start into taking part in this first flight contest. We run these contests every other week and they last for 1 week long. So last week's we had Dating That, and that was a Solidity repo. What I always say to people is to just head through Updraft and then take a look at these first flights, work through a few, and once you've got your confidence, then head over to the actual contests on Codehawks with the competitive audits we have coming up. We've got a lot of exciting things to come. We have 2 contests live at the moment. We have Gamma and we have RAAC. We are currently judging some contests as well, so some rewards will be paid out within the next couple of weeks. And if you do want to get involved, we have some contests launching very, very soon, so make sure to keep an eye on that. But that is all we have for today. I thought I was sharing my screen then, but I wasn't. Doesn't matter either way. We have some very big contests coming very soon, so make sure to keep an eye on the Codehawks platform. But that is all for today. So thank you very much for joining this stream. I hope you have enjoyed, and I hope it has been helpful. And I look forward to speaking to you all in the Discord and seeing what vulnerabilities are found from this repo. But thank you very much for joining us, and we will see you all soon. Goodbye.